All right, hey everyone. My name is Vivid. I'm a PhD student at Penn, working with Michael Poza, and I'm excited to present on some work that we have on sampling-based MPC for contact-rich manipulation. We already know that humans day-to-day are extremely capable in leveraging contact when they're trying to do tasks all day. So these examples are people who are experts in their activity or their field. But actually, even the most mundane of tasks that people do every day, such as this person rummaging through a drawer of unknown contents, is actually quite skilled and efficient, despite not having any plan or even preconception of what was in the drawer to begin with. You can see they even use spontaneously some of the other objects in the drawer as a tool to help them open bags of other objects. We also know that robots are making great progress towards being able to do some of these very contact-rich behaviors enabled by TRI's recent work in diffusion policies, where this video came from. Though we also know, being in a model-based workshop, that some of the work like this requires human demonstrations beforehand. And so it's not clear how these robots are going to perform if they're asked to do some other task, or even if the objects significantly change from the demonstration to perform the same task. We can swap the assumption of having a demonstration beforehand with the assumption of having a model. And models can be more task agnostic than a demonstration. You can use models for all sorts of kinds of tasks. And in fact, in some previous work that Michael mentioned in more depth during his talk, we can actually build models quite accurately from scratch anyway. So maybe this is a better assumption that might be more realistic for some other scenarios if we want our robots to be able to do things in real time that maybe they weren't prepared to be able to do before. So really, we want a controller that shares a lot of the characteristics of this human rummaging example. It's demonstration independent. It's also contact implicit, yet it ends up being extremely contact rich, but we definitely know that that contact mode sequence was not planned ahead of time. And notably, it's real time. So we know that we can satisfy the first two of these if we formulate an optimization problem such as this with access to the model. The model is going to inform the nonlinear dynamics as well as some notion of how the contact dynamics are going to work. Here we wrote it in complementarity format, which means the contact forces are also a decision variable in the optimization. So you don't have to prescribe them ahead of time. They will be solved for when you're optimizing. Now, really, those two things that I already mentioned that give this the full expressivity are really the problem in terms of getting this to work in real time. So the nonlinear dynamics and the complementarity constraints can be quite problematic to deal with if you're trying to do this on the fly and in time to know what your next action should be. What people have done to get around the slowness of this is just replace these two things with something that's simpler and easier to compute really fast. Here, the example that I put up is we take a linear complementarity system, which linearizes some things, but still leaves the contact implicit structure. And this is exactly what Alp's work, C3, does, and is very similar to Simon's work as well. However, this model is local, so let's see how it performs if we use it. So in this example, we're going to have the Franca with a simple spherical end effector whose goal is to manipulate the ball to move in the direction indicated by the arrow. We see what happens is that robot does really one useful push, and then it just hangs out where it was, and in fact is sort of in the way of accomplishing more progress towards the goal. And we'll see on the next slide that this is actually because of the local LCS model really getting us in this position where we're stuck. So the work that's presented in C3 actually does this very example, but they're able to have much better performance that results in the robot returning back on top of the ball and doing one push after the other. And the way they were able to do that is by heuristics that bake in the fact that we already know that for rolling around a sphere, a pretty good location to put your end effector is right on top of the sphere. And then from there, we can roll out the contact-implicit controller, and it can do pretty well. It's not clear what these heuristics should look like if the scenarios become much more complicated. Specifically, if this geometry of the object we're trying to push around is more complicated, or maybe we're trying to do something that that currently requires being able to track a reference trajectory, but we don't have access to one. So while C3 does meet all of these requirements, the one that we need to add in is that we need the controller to be globally aware in some way. So let me show what it means to not be globally aware. In this scenario, our end effector and the object, pretty close to what the LCS is going to effectively do in this scenario, is just consider the point on the object that's closest to the end effector. It'll do the same thing for the object-ground interaction, and then it will assume that the object is the union of both hyperplanes, essentially turning this object into something like an infinite wedge. And this works pretty well if the region of the object you want to contact is pretty close to that tangent point. But if you want to do something like move your end effector to the other side of the object, it doesn't actually think you can do that because it thinks you now have to pass through the object to get there. And this is especially not useful if the goal for where you want your object to end up is on the side to the left. This means that the only way for the end effector to move the object towards this object goal is essentially to apply a negative normal force, which we all know, and in fact, the optimization knows it can't do since we're embedding it in Coulomb friction. So it'll choose to do nothing and stay where it is, instead of make the problem worse and bump the object further away from the goal. However, these LCS views are different depending on where the end effector is relative to the object. So here we show 4 different possible locations where the end effector could be, and the LCS simplification of the object geometry looks drastically different. Some of these are more amenable towards making progress towards the object goal, and this would be reflected in the optimization costs that C3 uses as we formulated before. So what can we do to leverage the fact that if we put our end effector in other places, we realize in some of these regions, we still can make progress towards our goal. We start with the full problem on the left, which is global but slow, and the C3 simplification on the right, which is local but fast. We're going to change both of these things and meet in the middle. The first thing we're going to do is on the left one. Let's just say we don't make contact at all. This means we're not going to be able to move the object really besides its own autonomous dynamics, but that means we dropped all of our contact-related decision variables from the optimization problem, and the only thing that falls out of our contact complementarity constraint is that the gap function should be non-negative. Now, because of these simplifications, even if we wanted to use the full nonlinear dynamics, this is significantly faster than it was before. It doesn't involve any contact between the robot and the object, but it's global in its collision avoidance optimization objective now. And in fact, even if we didn't want to use the full dynamics, it's fast to approximate because you can just use something like a weighted travel distance. Also notably, we're going to assign this an end position goal. So what should the state at the end of this trajectory be? This is what we're going to pass over to now the right problem. The right problem still uses local LCS dynamics and contact constraints, but that LCS is not local to where the end effector started. It's local now to the ending configuration of the left optimization problem. And because we didn't change the structure of this optimization, it's still as fast as it was before, and thus fine with doing it at real-time rates. If we sample potential values for this intermediate waypoint, and then we find the minimizing sample of the sum of these two parts, then what we end up with is something that allows your robot to explore globally. And then once it's at these different positions, it can act locally in a way that's fast. If we were to plug this into a closed loop controller, the secret sauce is really in this yellow block here. That's going to act as a switch between using the contact-implicit controller, C3 on the top, versus trying to move the end effector somewhere that's more advantageous towards making progress to the goal. So let's dig into what that algorithm looks like more specifically. First is we're going to generate a list of samples. I wrote this as being in the full state space of the system, but note that actually the sampling is even more simple than that. The only thing that we can really change if we're claiming that we're not going to make contact between the robot and the object is where the robot ends up. We don't actually have control over where the object goes. So here, the only thing that's different between all of these samples is the three-dimensional end effector location. So it's tractably small and physically meaningful. We're always going to consider the current configuration of the system as the first sample, and then the rest will differ only in their end effector location, but can be otherwise generated however you like. Note that these samples and their respective LCS simplifications of the object can look drastically different, particularly with more complicated geometry. For instance, like this jack example drawn on the board. Next step is let's compute the cost associated with each sample, as well as the next action if we were to pursue that sample. Recalling from the previous, from a couple slides ago, we know that the cost is going to be a combination of the C3 optimization cost from those configurations, plus some penalty on traveling if your end effector has to move to a new location in order to perform that control goal. If we use the first sample, the next action is just going to be the control input, the first one that was computed in the optimization problem. Then we take whatever next action is associated with the lowest cost, using some hysteresis between deciding to use C3 where you currently are and deciding to move somewhere else. We note that this is making hybrid decisions at two levels. The first level is it's going to decide whether to apply control where it is or move somewhere more advantageous. And the second level is when it does apply that control, it's still the fully contact-implicit formulation that we gave earlier. So here we're excited to show some very preliminary results in how this might work. Here we're using the more complicated jack example. And what we have is there's a goal in green on the left. The sample locations are these light blue dots. In this example, we're sampling on the surface of a sphere around the object. And the optimal sample, the best one that we might pursue if we are going to be in the repositioning mode, is in yellow. So what we see here is that it's going to freely decide whether to run C3, so the contact-implicit controller that can make and break contact, and decide to reposition to a new sample. You'll also notice that we're not even considering very many samples at a time, like one or two, but just the fact that we can run our controller at pretty fast rates, we're still able to consider a significant number of samples over like a second. With that in mind, some next steps for this project are to improve the performance on some of our simulation examples. We'd also like to explore some other sampling strategies. The one that we showed earlier may be considered a naive approach, just random sampling on a pretty low-dimensional 2D manifold. And it does seem to work surprisingly well, especially if we can consider a high number of samples over a fairly small amount of time. But maybe there are fancier solutions that will just outperform this. Namely, some samples that have been previously computed might actually still be valid in the current system configuration. So maybe there's something that can inform where to next sample based on previous samples that are still valid. And lastly, we'd be very excited to see this running on hardware and are eager to tackle any engineering challenges it takes to get that up and running. With that, I'd like to thank my collaborators as well as the organizers of the workshop. And here's where you can reach out to me if you can't ask a question now or catch me at the poster session. With that, I'll take any questions if there's time.